love to see people. I don't know
Okay,
if to see people.
so I'm very happy to be able to welcome Julianne Dalcanton here to the CFA today. Julianne is well known to many of you, and she was very excited to come here. So excited that she braved her way across the country yesterday into the teeth of the storm, but she made it here. Julianne got her PhD from Princeton and then was a Hubble Fellow at Carnegie Observatory before moving to University of Washington as a faculty member. And she's going to be telling us today about the Panchromatic Hubble Andromeda Treasury program.
Great, thanks. Can I get the lights down up near the front? Oh, awesome, thank you. Okay, so so we call this FAT. And so what is FAT? FAT is HST's wide area map of M31 covering from the UV through the optical through the near infrared. The reason why this is a little bit insane, there's the size of a full moon, okay, and the size of an HST frame is a tiny fraction of one of these. So this is a completely ridiculous thing to do. So the natural question you might want to ask yourselves is, why in the world would anybody decide to give a group of people 800 orbits to look at one galaxy, right? If you told me that, I mean, it was a really good proposal, though. So I'm going to show you why it was actually compelling. Okay, that this isn't really a study of just M31. This is really a study about foundational astrophysics. So everything we do in astrophysics is really about trying to understand detailed physical processes. And these are processes that happen on parsec, sub-kiloparsec scales. When we look at something in the Hubble Deep Field, we are not resolving the actual astrophysical scales of interest. We can infer them, we can come up with scaling relationships, but we're not actually talking specific energies and whatnot. And so what you can actually do when you look at something that's really nearby is you can actually measure what's going on with the subgrid physics. What we do currently is, it's a little bit of a rickety ladder, whether we're doing it in terms of simulations or we're just kind of looking at the broad scaling relationships. We're not actually measuring astrophysical quantities of interest. Those are things we can actually do if we're nearby, and I'll try to explain some of how that works. The other question is that this is really not so much a program about M31 as much as it's about M31's stars. That when you look at a nearby galaxy with HST, it resolves into absolutely millions of stars. So what I'm going to do is I'm going to show you one square right in here. So this is an image that was put together by Ben Williams and Zolt Live, and we're going to zoom into it. I had the good fortune to marry a film video producer, so I can order these things up at will. So we're going to zoom in, and then we're going to pan across it. Hold on to your cookies. And you can see that the mix of stars, their colors changes, their distribution changes, their luminosities change. You see modeling that's due to dust. You see brighter foreground stars. Here we're starting to get into a dustier region, but you're also seeing, not surprisingly also, a lot of bluer, more luminous stars associated with it. And this is just one, you just saw a tiny fraction of the survey area. So we have this data for, I like to say 1/10 of a billion stars. Okay, and we have it from the UV to the near infrared. And they're all at the same distance. It's not like trying to do this in the Milky Way. So when you look at M31, every single star you see, you no longer have that question about, is this one fainter than that one? What's the foreground? It's all the same. Okay, and so suddenly these comparisons become amazing. The other thing is, if you got 100 million stars, you can really start looking at kind of rare types, fast phases. M31, it's been around for a while. We have surveyed it within an inch of its life. So you want to know where the Wolf-Rayet stars in M31 are? Somebody's cataloged them. You want to know where the supernova remnants are? Somebody's cataloged them. It also, within one galaxy, you span a very wide range of metallicity, that you've got extremely high metallicity populations in the center of the bulge, and then you have intrinsically lower metallicity populations as you go outwards, and also mixed throughout. And it's so big on the sky that if you look at it with HST, you can resolve physical processes going on the scale of tens of parsecs. Okay, and these are interesting astrophysical scales. This is no longer standard extragalactic kind of kiloparsec scale patches. These are really starting to get into scales of interest. Okay, so what did we actually do? So this was 828 orbits executed over 4 years. We just finished in late October last year. So the previous large HST program I ran, the camera literally, part of it exploded 4 months into the program. So the fact that I actually made it through this one is a miracle. We organized this into what we call bricks. There's 23 bricks. This is superimposed onto a galax image, which traces the star, primarily the star formation. You can see there's this very, very strong 10 kiloparsec star-forming ring, but there's also kind of inner rings or tightly wound spiral arms as well. The bulge is actually bright in the ultraviolet because it's got this population of extreme horizontal branch stars in it. We've been able to study those as well. I think this is going to be the lasting legacy of it is that it really covers from the UV all the way to the near infrared. And we just don't really have that many views of stellar populations that span that wide range of wavelength. Now, why do you actually need this? It gets you a lot of different things. So here is our filter coverage. We've got 2 filters with UVs in the ultraviolet, 2 optical filters widely separated to give you a lot of leverage on stellar temperature, and then 2 standard high throughput near infrared filters. The reason you want this whole range is that you have hot stars where they're emitting most of their flux in the ultraviolet and then practically nothing in the near infrared. You have cool stars where it's exactly the opposite situation. The optical is great because you get kind of just a lot of broad leverage on stellar temperature, but these also help you in terms, these filters do some additional nice things for you that I'll talk about. The observing strategy is we observe in these bricks. Each one of these bricks is a 3x6 tile of WIFC3IR frames. So we take one orbit in WIFC3IR, then we take another orbit with UVIS. While we're doing that simultaneously, we're running ACS in parallel. So while we take this frame in the primary, we're taking this frame in the optical. So we step around in a 3x3 grid. 6 months later, we rotate the telescope, and we do the same thing on the other side. Okay, so it's an extremely efficient use of the telescope time. Okay, so in terms of characterizing stars, getting this 6-filter photometry, it gets you obviously a lot of leverage on stellar temperature. It also gets you a lot of leverage on the dust, that we're sensitive not only to the amount of extinction you can get, we're also, turns out, we were not really anticipating this, but we actually do have some sensitivity to the actual extinction law itself. And this, what this means is that we can actually constrain the properties of the actual, the more fundamental stellar properties for hundreds of millions of stars. So this is just results from SED fitting of some, this is just a small subsample of it, where the stars have been fit and simultaneously fit for the extinction and the underlying stellar properties. They're color-coded according to mass, and you see obviously things nicely drop out along the main sequence. You get high mass stars down to low mass stars, lower mass stars on the RGB, AGB stars, going to higher masses at higher luminosities. So this is all coming out of it. The other thing that you get with this is that it allows you to infer the flux at wavelengths you didn't actually observe. Right? So if I take a star, I fit a good model to it, I can tell you what the ionizing radiation that came out of that star is to a first approximation. And also I can do that even if there's dust in the way. Right? I mean, I can actually, so that what this means is that you can actually start inferring useful things about energy budgets in specific wavelengths. You can say, how much ionizing radiation there is compared to its effect on the ISM. So this is something where it's giving us a lot of energy information that couples directly into ISM studies. And I think this is going to be one of the really exciting things. It's a long lead time study because this is hard, but we're getting there, and I think it's pretty exciting. So this is our current coverage. This was a lot more interesting to plot to show when it was just a couple of them, but now it's just a big green splotch, which is fantastic. All of the photometry has been publicly released. And it's our first, we're doing multiple generations of photometry, so this is our first generation of photometry. But you want to use any of this, it's all out there. Like I said, we have over 100 million stars. A lot of these, because of the overlaps, some of these have been imaged multiple times. So we actually have, for some of them, you can actually do some time series kinds of stuff. Not optimal sampling. I mean, it's kind of weird sampling, but you can do a little bit of it. We also, we measure all kinds of properties for these stars. So we have, fit quality and whatnot. So there's tons of stuff. There's papers describing what's actually in all the photometry packages. We're now that we're at a point that we're complete, we can start stitching these things together into large area maps. And so Cliff Johnson and Amit Kapadia, who worked for the Zooniverse, actually have put this into sort of Google Sky kinds of visualizations, so you can zoom down into these things, and it's pretty cool. I'm going to show you I'm going to do a flyby of some kind of pictures of individual bricks along the main sequence, stepping outwards in radius. Zolt Live is one of the people who does fantastic imaging for Space Telescope. Ben Williams made the actual mosaics, and then Zolt made them all purdy. You can actually see that little blue spot in there. That's the double nucleus in M31. M31's bulge. You can see the modeling. These are UV, 2 optical and 1 infrared filters. You can see the modeling due to very light dust in the bulge. This is going out. This is kind of the first modest star-forming ring. There's a little bit in here. The next one is brick 15. Brick 15 goes right on the major axis, goes right through this 10 kiloparsec star-forming ring. You can see all the dust. You can see all the blue star-forming regions. And then this is in the outer disk. And again, this is actually through another star-forming region. You see a lot of blue stars, but it's much lower stellar density as you go through this. Now, this change in the stellar density is really a big deal for the survey because a lot of our ability to measure photometry depends upon crowding. This is a very different situation than just trying to measure standard extragalactic photometry, where you take an image, you've got lots of sky, you draw a little aperture, and you measure the flux. This is something where you have to simultaneously model and iteratively model all of these stars. So you have to find the stars, and then you simultaneously fit their fluxes for a point spread function model and iterate this until you come up with an optimal solution that simultaneously fits the flux in all of the different filters. So this is a really complex kind of thing. And the reason it's complex also is there is no sky. Even here, I don't know if you can see, there's low-level modeling. So this stuff that's sky, even that's not sky. So all of this is what we call is highly crowded. This data is difficult to deal with technically, presents a number of challenges, and photometry in this kind of regime is tricky. The other thing about this kind of data is that every single part of this has effectively the same exposure time. And yet, in spite of it, in the bulge, we can only see the very brightest stars compared to the outer regions. There's almost 6 magnitudes of difference in terms of the depth we can get to as a function of radius. And the reason is it's a little subtle, even though these all have the same exposure time. Basically, at a given telescope instrument resolution, pixel sampling, there's a certain number of stars you can cram onto your image before they all overlap and you can't pick them up. So what happens is you can do photometry until you get down to that certain number of stars per square arc second, and then you're done. In a high surface brightness region or a distant region, you reach that much higher in the luminosity function. You reach that maximum packing. Whereas if you go to a sparser region, a nearer galaxy, things are a little more spread out and you can go fainter down. Okay? So this is another reason why M31 is that it's really, really close. And so we can beat the crowding limit in a way that we couldn't if it were even twice as far away. Okay. This is the data right here. This is the limiting magnitude for the ultraviolet. These are the limiting magnitude for the 2 optical filters. These are the limiting magnitude for the 2 near-infrared filters. The ultraviolet, the data is not crowded at all. Ultraviolet sources are very sparse on the sky, except maybe a really slight upturn right in the very central fields. But here, you really do see what you expect. All the exposures at the same time, you have the same limiting magnitude. Whereas the behavior here is very, very different. In the optical, it starts to get flat in the outskirts. So here, we've gotten to the end of the crowding limit, and we're photon limited. But in the near-infrared, you're hosed all the way down. However, the recent advance, and this is not the version of we haven't finished this photometry for the whole survey yet, but we're really, really close. We're starting to do some advanced stuff where we're actually, previously what we had to do was reduce camera by camera by camera. Each one of these cameras have different distortion corrections as a function of time, complicated overlaps. And so you can't, in order to do this point spread function fitting where you're modeling the entire image stack, you need to have astrometry at an absolutely exquisite level. And by exquisite, I mean excruciating, horrible. But Dustin Lang is amazing. So he's one of the architects of astrometry.net, and he's worked with us on this project. And he has this stuff aligned to 10 milliarc second precision. It's unbelievably beautiful. And this has allowed us to do this photometry. We always thought it was possible. We wrote in the proposal that it was possible, and it is, in fact, possible. So what we're doing is, so now we're using all the information. So because the optical data is very rich in stars, but better resolution than the near-infrared data, we can kind of leverage the information that we know where the stars are in the optical data, and that allows us to do better modeling of the near-infrared. So when we just do just the IR data on its own, we don't do so well. But when we actually use the fact that, like, I actually know this is 4 stars suddenly we can get almost a magnitude and a half deeper. And so this is what's coming out the pipe. So those limits from the previous page are now going to be about a magnitude and a half deeper. I mean, yes, the errors on this, the uncertainties are significant, but it still looks, this is actually a well-behaved red giant branch, so it's working. So this is also work by Andy Dolphin and Ben Williams. So the main data products that come out of this is 6-filter photometry, this unbelievable astrometry from Dustin Lang, a lot of software. So all these photometry packages are publicly released so that whatever we're developing, it's getting out there. Calibration, right? When you have this many overlapping images, by gum, you absolutely, you can really figure out your flat field to a high level of precision. So there's a lot of stuff where we're calibrating it and passing the information. Dustin found things like there was like a 0.9 degree difference between the angle of the parallel between the two cameras on the thing. We found slight errors in exactly what the chip gap is like in ACS, right? I mean, really low-level stuff, but we're picking it out. Also, a lot of ancillary data. So we've, Raja Guhavakirta's group is doing extensive DMOS spectroscopy. Adam Leroy has been, and Andreas Schruba have been leading ISM studies. Karen Sandstrom has been doing Herschel spectroscopy to actually look at energy flow and cooling stuff. So we have a lot of other data that we're bringing in with us. Okay, so what does the data actually look like? The primary way that we look at this stuff is through color magnitude diagrams. So this is the ultraviolet. This is 275, which is kind of like the near UV filter of Galax, and this is kind of a classic U-band. Over here, so this is always going to be real data, and this is going to be that new 6-filter simultaneous photometry. This is just a simulation actually from the original data paper using the older photometry, where the points have been color-coded by age. Okay, so in this case going down to 750 million years, up to 5 million years for solar metallicity. And so you can see you've got a well-developed main sequence here. This is broader than here because this doesn't include dust, whereas the real galaxy actually does. There's this swath of stars here that you actually see over here. These are blue core helium-burning stars for metal-rich populations show up over there. The data quality in the opticals is absolutely bonkers. Here you've got the main sequence, red giant branch. You've got a red clump. You can see it's extended out by dust. There's an AGB bump. Tip of the red giant branch, AGB stars. You've got some galactic foreground. You have some red helium burners. This is really fantastic data. And if you look at just the color coding on the equivalent age thing, we're getting down to main sequence turnoffs that are like of order a gigayear or more, okay, in the outer regions. So this is from some of the lower density regions. In the higher density regions, this is actually going to move up a bit, but it's still pretty good even in the inner parts. Okay, so what we can do is we can take data like this and then say what linear combination of this kind of data completely folded with all of our observational errors produces CMDs like what we actually see. And this is how we derive star formation histories. So we take a region, we look at the color magnitude diagram, we model it as sums of this convolved with observational errors, and that derives some star formation history. So now that the survey is nearly complete, so Alexia Lewis is a grad student at UW, she's taken this whole survey area and broken it up into 100 parsec regions. So each one of these is independent from the other. And then within each one, she solves for the star formation history. So even though every one of these is solved for independently, you can see that there's large-scale coherent structure. This is a movie, starts about half a gig year ago, and then goes forward. And you can see that 10 kiloparsec star-forming ring, it's really long-lived. It's just sitting there. Like we were expecting, it's a highly inclined spiral arm. It's going to be propagating, or maybe it's a wave passing through the galaxy. It's going to be moving. But the the rotational time here is about 250 million years. And it's just kind of sticking there. We haven't done like a really detailed, it may be that we may be able to pull out some degree of movement, but at first order, that structure is really just kind of sitting there, which was not really what we were expecting at all. So Anil Seth at Utah has been simultaneously, again, now that we have the data, the full data set, he's just been looking at overall surface brightness, surface density distribution. So he's basically been identifying consistent sets of red giant branch stars and then just plotting their density. And so this is what's actually observed. He's fitting with just, at this point, a very, very simple kind of double Sursic model. And when you subtract it off, you always find a very significant overdensity, kind of like at the 30 to 50% level, associated with that 10 kiloparsec star-forming ring. And it doesn't, this is, yes, you could argue, there's structure on these scales, and maybe he should do a different fit. It doesn't really matter what he does. He always gets this big overdensity sitting right there. So there's clearly some kind of dynamical thing going on inside this galaxy where there is a long-lived density enhancement that is associated with long-term ongoing star formation. So this is very early. We don't really understand what's going on with this yet. And I said this wasn't a survey about M31, but we'd be fools not to do this because this is kind of fun. Okay, so this is this is the part of the talk where it's what I've personally been kind of working the most on, and it's mapping the dusty interstellar medium. And this is very much not what I was planning on doing, right? This is kind of science at its best, where you notice something, and it kind of it just tickles your interest, and then you follow it, and all of a sudden, you're an expert in cataclysmic variables, right? You had no, how did that happen? Okay, so this is the work. Morgan Fouy-Snow, there's other people who've been involved as well, but Morgan is a postdoc at University of Washington, moving to MPIA. Okay, so the one thing I haven't showed you yet are near-infrared color magnitude diagrams. And so these are just what we published in the first data paper, with just kind of the first initial data that came in. And you can probably see it best over here. So this is brick 15, which is that kind of dusty star-forming ring along the major axis. You see this very, very narrow red giant branch. And then you see stuff coming off to the side. Okay, so this is the red giant branch, and the red giant branch is extended to the red. And you can even see some of it here. It just doesn't show up as well in this representation. But it's more than just kind of extended. It's actually doubled. So this is if you take a single WIFC3 IR frame and you break it up into just 16 different regions, and you plot the color magnitude diagram in each of these regions. And you can see that in every case you get this relatively narrow feature that always stays in the same place, and then you get this second blurry feature that moves out all over the place. And so what happened was, this was not too long after we started getting data, I was asked to give a talk on this in this HST meeting in Venice. And so I'm like looking at the data, like, what am I going to show? And you see this, and it's just like, this is not anything that stellar populations can do, right? This is not these are old stars, and you do not expect, 100 parsec variations in old stellar populations. Those should be very, very well mixed. And so what became clear is that this is actually just the effect of dust. So what's happening is, if you imagine that the stars are in a thick layer and the dust is associated with the gas and is in a very thin layer, you see a population of stars that are in front of the dust, and that's this. And it's in the same place every single place, because you're just seeing those unobscured red giant branch stars. And then this stuff over here is all the stuff that you're seeing behind the dusty layer. And because the dust is associated with the gas has structure on scales down to sub-parsec, you can have very, very rapid positional changes in what's going on with the dust, even though the underlying stellar distribution is quite smooth. So this complicates interpretations of CMDs, and this has actually sort of slowed down some of the star formation history work, just because this is so complicated to deal with in terms of modeling it. But it's a really good way to study dust. So what I took on was starting to try to understand dust. Now, there is a rich literature, especially in the Milky Way, and a lot of people here at Harvard, so Alyssa Goodman, Charlie Latta, Lombardi, Julianne Leyland. There's a lot of people who've done a huge amount of work with extinction mapping in the Milky Way. This is something it's largely done in the near infrared, done with 2-mass, and it's got lots of great features. So if you can map the extinction of dust, it gives you a pretty good probe of the total gas column density. So within a given region, if you're assuming that you're looking at something that has a relatively uniform dust-to-gas ratio, making a map of a molecular cloud is really telling you something about the total gas column density, whether it happens to be emitting CO or CN or whatnot. It also makes it a really nice complement of emission studies of the gas and of the dust, so that you can say, how does the total column compare to where I actually do CO, do CCO, or where I actually see emission from the dust. And within the Milky Way, these kinds of extinction maps have shown to have a really quantitative connection with star formation, that people have been able to identify that there's certain extinction thresholds that tend to be associated with the formation of molecules, with the formation of stars. So this background are maps of the Orion complex from Lombardi et al. 2011, but there's dozens upon dozens of excellent papers that could be cited about this. This is just illustrative. Okay, so on this particular plot, I've just highlighted a couple of things in terms of color scale. So an AV of 1 is sort of a very, very light beige. AV of 3 is kind of medium. AV of 5 is where it starts to get a little bit darker. Typically, this threshold of AV of 1 is about where molecular clouds go from being translucent to not, and you start seeing CO. Once you get well above an AV of 5, that's where you start to get some of these really dense gas traces that seem to be much more linearly related with star formation. So the other thing I just want you to note is that on this scale, I'm going to talk about 25 parsec scale regions in M31, and so I just want you to have some idea about, what 25 parsecs might look like at a typical distance of Orion. Okay, the other thing that's known about these molecular cloud regions from studies that have been done in the Milky Way is that in general they have log normal distributions of extinction. So that if you take this whole region and you make a histogram of how many pixels there are at every possible extinction level, you wind up with something that looks like this, that it's a log normal with a well-behaved peak and then a long tail towards high extinction. This is work by Julianne, who also thinks that in general that there is also an excess you tend to find in the star-forming molecular cloud. So it's not a perfect log normal. In the ones that tend to have star formation, you maybe get a little bit of an excess. But in general, a log normal describes a large fraction of what that dust distribution looks like. So Junie actually gave me one of his maps, which I subdivided into sort of approximately 25 parsec scale regions. And then within each subregion, I've plotted the histogram of all the pixel values. And you can see that in large numbers of these, a log normal is a pretty good representation. The log normal does start to break down when you look at these regions where you have kind of the highest contrast and filamentary stuff. And so you can kind of see maybe why you get this tail in regions where you start having these kind of caustics in your dust distribution. Okay, so the thing is that this log normal distribution of dust modeling the background view of the stars is probably what's going on in those color magnitude diagrams we're seeing in M31. And so we're going to now use that to try to infer what's going on with those distributions of reddenings within M31. So what we do is we take regions on the scale of a brick, and through the magic of Keynote's table function, we divide it up into 25 parsec regions. These are about almost 7 arc seconds on a side. And each one of those is probably sampling a region that would look like this in the Milky Way. That if we had infinite resolution and dust vision, we might see an extinction pattern that looked like this. So this is the Taurus molecular cloud. So we don't actually see this. Instead, what happens is we measure the colors and the magnitudes of, in each region there's of order 80 to 100 stars that falls in a 25 parsec square box. And within this region, we measure the colors and magnitudes of all of these stars. And so these stars, what they're going to do is some fraction of them are going to be in front of the dust layer, and those are just going to look like normal RGB stars. Some fraction of them are going to be behind, and those ones that are behind are going to be sampling this dust distribution. So this star that fell on this line of sight would be highly reddened. This star that fell on this line of sight wouldn't be reddened at all. And so we're not going to be able to say for sure which one star is associated with what, but we can analyze the distribution and learn something about what are the statistical properties of the dust within that 25 parsec box. We can't map it out as beautifully as done in the Milky Way, but we can infer some broad statistical properties. So for example, here is Junie's map of the Orion Nebula. Here it is if you divide it into 25 parsec boxes, and then you step them by 12.5 parsecs to just kind of Nyquist sample the features and then plot it again. And this is, say, the median within each grid. So within this box, what's the median AV that you get? And it makes this map. And you can see that it basically gets the broad structure that the highest extinction region is in here. There's a little bit of a shape to it. And that's if you take every single pixel in a grid box. But it turns out if you take only 25 per box, 25 samples per box, you still kind of get a lot of it. Like you maybe miss some of the very highest features on any one realization of it. But in general, even with 25 samples, which is fewer than we actually have in most of our cases, you still do remarkably well just sampling the distribution. Yeah, yes, you're not going to be sensitive to some details of the tail, but in terms of like what's the median AV in a 25 parsec box, we can get that. Okay, so operationally, what we're going to be doing is we're going to be modeling the color magnitude diagram like this. We're going to be modeling it with the sum of a red giant branch that's unreddened plus a red giant branch that samples some log normal distribution of reddening behind it. So the way this works is that within each 25 parsec pixel, we fit the color magnitude diagram. And so we fit it plus this foreground plus a log normal. We fit for the median AV, we fit for the width of the log normal, and then we also fit for the fraction of stars that are in the reddened peak compared to the unreddened peak. This turns out to be really interesting in the end. So here's an example. So this is our model of the unreddened peak, of the unreddened RGB, and you can see that all the stars are redder than it. So if you actually build this model, this distribution is very well fit by a median reddening of about an AV of close to 2, a very characteristic width of the log normal of about 0.4, which is really typical of what people see in the Milky Way, and a reddening fraction where about 75% of the stars are in the reddened peak. To build these local models of the unreddened CMD, we do this empirically rather than fitting a functional form because the intrinsic CMD is really complex. So what we do is we, in bins of constant stellar density, which captures all our observational errors very well, and also is a nice proxy for radius, we then identify regions that have the narrowest RGB. We then also cross-correlate those with Bruce Drain published a map based upon dust emission. So we also cross-correlate those and reject any point that also has significant dust emission. So we're just trying to find the cleanest, most dust-free things to use for our model. These are not a fair sampling of the galaxy. Okay, and so we do have some slight population things, but as I'll show, the population in the RGB is really very, it's pretty well behaved. So it's not as tragic as it might be. And I think we can do some advanced modeling things to fix it. So that, there are just certain regions of the galaxy where there happens to not be much dust, and these are they. These are what the resulting RGB in these as close to zero extinction as we can get them regions look like as a function of surface density. So this is in the inner galaxy moving outwards. You can see how the data gets fainter and fainter because we're doing better with that crowding limit. But it's very, very thin. It gets a little broader as you go here because the crowding adds additional photometric errors to things. The other thing I want you to note, the arrow shows you an AV of 5. So we're quite sensitive in the near infrared to very, very, very large reddenings. Okay, that if there were an AV of 10, we probably couldn't say much about it in the inner regions, but in the outer galaxy, we definitely would be sensitive to it. The other thing I want you to note is the width of the RGB. It's very, very narrow intrinsically. It's limited by photometric errors in some regions, but in the uncrowded regions especially, it's incredibly narrow, which means that even a relatively modest amount of reddening is going to take it out of the main distribution and will be sensitive to it. However, it also sets a floor that this method is going to suck at low reddening because we're going to run into the limit where the width of the RGB is pretty low. Okay. You can look at the properties of the RGB. This is the color magnitude of just the main locus, so basically the ridge point of it. Where it's color-coded, this is the inner galaxy going to outer and outer galaxy. And you can see it's very, very smoothly changing, and it doesn't change by a whole lot. So this thing of having few sampled regions, properly interpolating over them isn't a bad match to trying to figure out what the unreddened CMD is. Here's the width of the RGB as a function of magnitude. And so in the bright regions, the narrowest it gets is about 0.025, which as far as we can tell is about the limit of the photometric errors. So the intrinsic RGB in the near infrared actually may be narrower than that. This is also why this method doesn't work very well in the optical, because the optical, there's a more natural spread in terms of AV. So this arrow is about 0.25 AV. So generally, results at the level of 0.25, you just shouldn't really trust them because you're limited by the width. Okay, so here's what you get. So here's a map of the median AV roughly corresponding to this region over here. I don't know if you can see, do you see a little bit of kind of striping square structure just popping up in here? That actually turns out to be sort of 1.5% errors in the flat field between the two filters. So we were sensitive when I said that we can really do a lot of stuff with calibration, like I think I can actually make this better by doing a better job on the WIFC3 flat fields because we wind up being sensitive to it. So this map is basically, it's 12.5 parsec sampling of 25 parsec native resolution. Here's a comparison to an optical image. And a lot of these very filamentary structures you see here, really, they match just one-to-one with what you actually see here. Now, how does it compare with other dust tracers? This is the state-of-the-art dust map that Bruce Drain published. And it's a lovely piece of work based upon modeling all the Spitzer and the Herschel and the 2MASS data for M31. And you can see that what we have is significantly more resolution. All the features match beautifully, but the resolution that's available here is much, much better. I think the Drain map is almost certainly better at very low extinctions for those regions that I was saying that I think our technique we're just not sensitive. So in the low emission, I think this is superior. At low AV, this is superior. But I think the resolution gain doing it this way I think is incredibly useful. It also maps very nicely with the H1. This is another region. So this is that outer star-forming ring. This is that 10 kiloparsec ring. Again, beautiful matches, faint little filaments popping out all over the place. This is really, I'm trying to sell some dynamicist on this. This is, the bulge is kind of right here. Look at these little spurs and filaments coming off here. This is something where dynamicists have known that gas does this. And this has a very clear wavelength dependent. It's got a real clear spatial wavelength dependent that presumably is telling you something about dynamical instabilities in the gas and the gas here. And they're much more tightly wound than in the simulations I've been able to find of this phenomena. So I think there's something interesting there for someone to model. But I mean, they're just neat. So it has superb agreement with the dust morphology from emission, which is really amazing. I mean, every single one of these pixels, well, every other one is done independently, okay? And yet they are tracing exactly the same very large-scale structure here. I mean, just one to, if you just look at, see how that has like a little hook right there? That's that little hook right there, right? That tails off that way, that tails off that way, right? I mean, it really is a remarkable level of agreement, which I think is a tribute to both methodologies. The problem is that was a little bit of a cheat because I did not show those previous plots on the same scale. So in the mapping that Bruce does is that he builds a very complex model for the dust. It's calibrated off of stuff in the Milky Way. And then for that dust model, he can say, for this amount of emission, I would see this amount of extinction in AV. And so if I use that conversion, and Bruce and I have been in contact about this, the amount of AV that's inferred from his model is more than a factor of 2 times greater than what you actually see by looking at the actual reddening of individual stars. And there's not that much uncertainty. We haven't measured AV. What we've measured is reddening in 2 near-infrared filters, but that conversion to AV is pretty stable. It doesn't it's got 10 to 15% uncertainties in terms of variations in RV. So that's not factors of 2 and 3. So, further evidence that this offset isn't really, it's just not feasible. So this is the best fit model for a region. I think this is probably the one that we saw before. This is the probability distribution. So we do Monte Carlo fitting of the models in every single pixel. This is the model for the mean AV. There's nothing you can do that's all of a sudden going to say that I mistook 4 AV for actually being 2 AV. It's just not feasible. This is what it looks like if I just say I'm going to multiply the AV by roughly a factor of 2. It's just not consistent with the data. I could maybe get a change in the mean AV by just making it a very broad log normal. But again, I can't make it broad enough and have it be consistent with this, and it's also just a terrible fit to the data. So there really is something off with these emission models. And it's a little bit worrisome because this is, the primary tool that has been widely used to interpret what's going on with dust masses and dust emission when dealing with the SING survey or the Kingfish surveys. And those models there's clearly an issue with the normalization. The relative stuff is beautiful. The normalization is off. And this is not the first time. The same tension is evident in comparison with the Planck data. Other people have dust models that also report this tension. There's also tension when people are trying to measure inclined galaxies. what they do is they make predictions for what the emission is, and it's the same sort of thing. That basically what's happening is the real dust is putting out more emission than the models actually say that there is. So the dust is more emissive for a given amount of extinction. And I think I got the sign of that right, given the fact that I took a red eye. So, okay. So I think that right there is a really interesting result, and I think that's going to be, that shows kind of the success of having multiple different approaches, that each one's going to be better, right? We used Bruce's phenomenal maps to sort of build our confidence that what we were doing was actually sensible, but likewise what we're doing, I think, is going to help them improve their calibration. The other thing that's really natural to do is start comparing this with the gas. If you just take so if you make a map of the total gas column density combining both CO and H1, and you use standard Milky Way AV to NH1 conversions, there's no normalization problem. Normalization is just bang on with the Milky Way expectation. So that looks really beautiful. What's kind of fun, though, is that Andreas Schruba has been doing some really heroic mapping with Karma, where he actually is getting better resolution. He's getting down to individual molecular cloud scale. So he's got even better resolution than these 25 parsec resolution maps. And if you look at the CO, I mean, see that little hook right there? That's that little hook right there, right there. I mean, that we're getting this really beautiful level of agreement between a lot of what's happening with the individual molecular cloud structure and what we're seeing with the CO. And so this is going to be a really useful avenue in terms of trying to understand, dark clouds, yada, yada, yada. It is kind of interesting, though, because it's not actually perfect, right? This is a plot this is another region in the galaxy, and this is showing some extinction contours. So the underlying map is one of Andreas's maps. I think it's a relatively older fig, so this is probably an earlier reduction of it. And then the blue lines are the AV, and you can see, again, the agreement is really, really good. And then there's one corner where there's a lot of dust extinction, but there's just no CO, right? So everything looks great, and then in a certain region, it doesn't look great at all. It's like a totally different XCO factor in that region. And so one thing is that I think this might actually be a part of what's going on, or actually, I think we might be able to probe some pressure effects. Because this is a plot of the reddened fraction, the fraction of reddened stars. And in this corner, there's a very, very sudden jump in the reddening fraction. And the reddening fraction is sensitive to where that dust is along the line of sight. And so if you have gas that's off the midplane, you're going to have a lot of extinction. You can have a higher or a significantly higher or lower reddening fraction. But that gas is no longer going to be experiencing the full midplane pressure. It's going to be at lower pressure. So there might be some interesting things, I think, that could be followed up in terms of trying to couple these two different things. But I want to show you about another really fun thing that came out of this fraction of reddened stars. So when I was first doing this, I'm being a proper Bayesian, and I'm putting priors on stuff. And what's the natural prior on the fraction of reddened stars? It should be 50%, right? I've got a gas in the midplane, half the stars are in front, half the stars are behind. And I started fitting some of these bricks over here. And it kept on, even though I had a prior that was at 0.5, it kept on wanting to shove it down to these values over here. I was like, I screwed something up. And then I started doing more and more, and you could see that there was actually this larger structure in here. So I just want to go through what this is. This also, just note, this isn't a change in the fraction of reddening. This is a distinct axis in the fraction of reddened stars, right? If you go back, again, this is something where it's different. And this also, if you look at M31, one side of it looks dusty and the other side doesn't. Okay, the side that looks dusty, the reason it looks dusty is it just has a higher fraction of reddened stars. It doesn't actually have a larger fraction of dust. Okay, so I just want to explain where this is actually going. Okay, what this is that this reddening fraction turns out to be a really good probe of the three-dimensional tomography of gas and stars. So part of it is it can show you that local deviations from the midplane, but it also turns out that it's showing us something about the large-scale structure of what's going on here. So if you have a thin stellar disk, you get my expectation when I went into it, which is that should be 50% of the stars are reddened. So basically, for an inclined disk, relatively narrow, you have about the same number of stars here as you do here when you're looking at it, and so you get 50% of the stars. But when you have a thick stellar disk and a radial gradient in the stars, if I'm seeing stars along this line of sight, I have more, the unreddened part is seeing the inner regions of the disk where the stellar density is higher. And the part that's reddened is actually probing larger out in radii. And so it's got a smaller fraction of reddened stars. Whereas on the other side of the galaxy, you see exactly the opposite. The side that's obscured is probing closer to the center, so you have a larger fraction of reddened stars than you do here. So if you have an intrinsically thick stellar disk, you're going to get these offsets between one side of the galaxy and the other. You're also going to get effects that depend upon inclination, right? That if the inclination along the line of sight is face on, you're going to get smaller differences between the near and the far sides of the galaxy. So what this means is this gets you a two-dimensional probe of the thickness of the disk in compared to the radius and also the inclination of the galaxy. So this is the reddening, the fraction of reddened stars isolated to regions where we think we have very, very good quality data. Okay, so places where it's high extinction, low reported uncertainties. And you can see that very clear gradient that's right in there. And then here's a model of an inclined disk that fits this. So what I've just done here, I've just done a simple gridding in position angle, inclination, and what matters is the relative scale height of the disk to the scale length of the stars, assuming a double exponential. So a radially exponential surface density and a vertically exponential distribution. And so from this, we get that the scale length is about almost 7 times larger than the scale height. And you can measure, HR you can actually measure from an actual image, and people have done this in many different contexts, and that implies a scale height of about 0.9 kiloparsecs, okay, which is really thick. So this is the first time that this has ever actually been measured for a galaxy that's not actually edge-on. And so if you just think about it, this is actually really kind of cool, right? So that we have a galaxy where we can measure the stellar populations, we can see, we can infer pretty well what the surface density is, and we now know the thickness. We have all this spectroscopy of RGB stars, so we can get the kinematics, and so you can really start to look at like the dynamical balance, which can then get you at the low mass IMF, for example, that we can actually weigh the entire disk using this kind of data. The other thing about this is that this is just pretty fat. Okay, means that M31 is kind of thick disk dominated. Like if you want to go to a simple-minded view where you're actually viewing a galaxy as a thin plus a thin disk, or you want to go to more Bovian, Rixian, sort of a continuity of different metallicity populations. This is data for the Milky Way, where it's looking at what's the characteristic vertical scale height as a function of scale length for, color-coded by metallicity, where the size of the dot tells you something about the fraction of the population. The scale heights that we're measuring in M31 are kind of like up here. Okay, whereas a lot of the Milky Way's stellar mass seems to be in this thin disk. So in a kind of more traditional decomposition by Jurek, only 10 to 15% of the local stellar density or column density is in the form of a thick disk. Here we're finding that's kind of the dominant component. Doesn't mean there isn't a thin disk, but the overall geometry is characteristic of the majority of stars being in the thick disk. This is also totally consistent. This is surprising, but it's actually consistent with the spectroscopy that's coming out. So this is work by Claire Dorman, who's finishing up her thesis at Santa Cruz. And so, really, we've got like more than 10,000 Deimos spectra all over this, so it's a pretty cool data set. And so in various regions, she's decomposed different populations. And the disk velocity dispersions that come out are like 60 to 80 kilometers a second. These are not, 15 to 20 kilometers a second. So that the RGB population really does have it's dynamically hot, which is consistent with what we independently inferred about the thickness. And honestly, right, this is the extended structure on M31. Is this a structure you expect to be like super dynamically cold? Like I would say this is a good candidate for something that's been knocked to hell. So I think it's an interesting result and it's a surprising result, but not surprising retrospectively. Okay. So I want to close just by, I just want to try to give you a sense of the kind of stuff you can do once you start picking apart these galaxies into the individual stars. I could sit here and I could give a colloquium every day for 2 weeks about interesting stuff that's going on trying to use this. I think the energy budget stuff with the ISM is really, really, really interesting. There's a really, really cool thing. But the problem is, the reason we got time to do this in M31 was that M31 was a place you could do this really well. The reason you could do it really well was that it was close. And because it's close, the average distance between two stars of a given luminosity on the sky, they're more separated out. But as I move that same galaxy farther and farther away, that angular separation of those stars starts to blend together, and they merge, and I can't detect them anymore. So going down to kind of the faint stars, getting that leverage, it then becomes restricted to lower surface brightness systems. You wind up having to do dwarfs. You wind up doing halos or outskirts of disks. You don't wind up doing the main structural body of a galaxy. Even in M31, we can't really say a whole lot about the center of the bulge. I would love to know what's going on at the center of the bulge. When you look at an elliptical galaxy and people take Lick spectra of those centers and there's unusual metal populations, we have an analog of a classical bulge sitting, few hundred kiloparsecs from us, and we can't even resolve that many of the individual stars right in the very center. It's atrocious. And there's nothing we can do. It's entirely set by the resolution of the instrumentation that we have. Okay? So this is something where I would like this to get better, because I think there's tons of really interesting stuff. I think we are just starting to really be able to exploit this multi-wavelength data set. Okay? And so if we're ever going to beat this, we need better resolution. Better resolution is the only thing you need, and it means you're doing interferometry or you're doing a very large aperture space telescope. Yes, you can do AO from the ground in the near infrared, but if you think back to those stellar spectra, you're going to learn an awful lot about AGB stars and red giant branch stars. And I like AGB stars and red giant branch stars. Those are great stars. I am fond of them. But that's not that much temperature leverage. You really need to push out in the optical if you're going to get the temperature leverage, and especially in the UV, which gives you a ton of leverage for a bunch of interesting stuff. You really need to be back into visible and UV wavelengths as well. So I'm spending a bunch of time right now working on, starting to think about large aperture space telescopes. This has been, Mark Postman's been running Atlas studies. The Europeans have submitted these programs to the last large ESA call. And it's something where, Hubble's not going to last that much longer. And do we want to live in a world where we can't do high-resolution optical imaging, right? We've gotten used to that. It would be like if somebody said, I'm sorry, on ground-based telescope, we're going to burn all the spectrographs. It's just, we're just used to having that. And we all know that the lead time for getting large missions approved is long. And so if we do not want to have a generation that has no access to large space-based facilities, we have to start talking about this now. Okay? So Aura has started a study that Sarah Seeger and I are co-chairing, and what we're studying, we've formulated now as the high-definition space telescope. And the idea is that if going from HST to a 12-meter in space at the diffraction limit, it's like the equivalent of going from an old tube TV to the state-of-the-art ultra-high-definition telescopes. Okay? That it really is, it's all about precision in terms of the kinds of stuff that you can do. It's really ridiculous. If you run the numbers, so here's a plot of Jason Tomlinson's involved in this and made this great plot. So this is the size of a resolution element in log as a function of log of distance. Okay, and this is showing the angular diameter distance at the diffraction limit for HST, for JWST. JWST is worse because it's operating at longer wavelengths. And then an 8-meter space telescope and a 16-meter space telescope. Well, the angular diameter distance has a maximum and then turns around. So you can, basically, if you have an 8 to 16 meter, you can resolve 100 parsecs anywhere in the friggin' universe. Okay, you can look at your galaxy at a redshift of 2 and measure the size scale of an OB association. That's really, really amazing. Okay, but then if you want to say, I want to go close, so here I'm like, Jason, why don't you make it going closer? Okay, and so here's like 1 kiloparsec, the distance of Orion. With these scale telescopes, you're getting down to 10 AU or better in major star-forming regions nearby. Again, what you could do with that is just ridiculous. And you could do this in an era where you would maybe have Athena plus. You'd have UV spectroscopy on something like this that would just kill anything you would hope to do because it's so much aperture. UV coatings are getting better. It would be hundreds to 1,000 times improvement in throughput compared to UV spectroscopy. The other thing about this is that this is exactly the same telescope that you want if you love exoplanets. Okay? So that if you put a coronagraph on this or a star shade in front of it, it's the same project. So it's no longer a question of Exoplanets wants a flagship. Everybody else wants their flagship. This is the same mission where you just add a little bit of extra on, and suddenly it's the best for everybody. Okay, so I'm very excited about this, as you may have guessed. So right now we're in the point of just basically building science cases and defining technical requirements. We've got a great crew of technologists on this, and they're like, well, do you need the diffraction limit at 400 nanometers or 500 nanometers? Do you need this resolution or that? I mean, so it's like down in the, do you need 50 picometer stability in your mirror on 1 minute intervals or 30-second intervals, right? I mean, like it's down in that weeds. If you want to contribute to that effort, we are more than happy to help. If you have some great thing that you think your congressman would love to read about, they're going to love reading about detecting atmospheres of habitable planets. Like they're going to like that. But it'd be nice to have something else in there for those of us, the old school ones who are not yet working on exoplanets. So come talk to me. There's also a web page on the Aura website. They'll provide links to that, and you can contact any member of the committee. We're more than happy to talk about it. We'll have formal things where you can submit freaking white papers, but I'm at this point more interested in one-on-one conversations about what you can do with this. Okay, so the summary, there's just tons of data, and that I really do think with that, yeah, and yes, I am a convert, but I really think that what we're probing into is really stuff that's really new, right? I mean, that this is just, we've never had data this way. We are fully in the big data regime in terms of how we're treating this stuff. And this is new terrain for stellar astrophysics and for really astrophysical processes where you can couple timescales and energies to things, where you have the full galactic content, multi-wavelength, from the X-ray through the radio and submillimeter. And there's also this isn't even a complete list. There's other people I should have added to it, but there's just a ton of really great people working on this project. So thank you guys very much.
I have a question about this disagreement between the AV estimates. If you take the galaxy and well-known Schlegel maps, they have a sort of independent check, the colors of red galaxies. If the AV to dust ratio was off by a factor of 2, we wouldn't have seen a red sequence. Here, how can you explain this? Is it possible to do a test like this? Because I saw background galaxies on your images. Maybe you can just measure the colors and tell what is right.
Well, I think so. Bruce says that there's somebody at Princeton. I think at Princeton, who Bruce was not surprised to see this discrepancy because there's somebody who's looking at background quasars in M31 and seeing exactly the same offset. Okay, and all of these. I mean, it's the same sort of thing. Whether you want to use it in background galaxies or quasars or stars. These are things where they're standard crayons, and I say that this has a different color than what the model says. So in some sense, they're all going to give the same offset. There's a lot of, in these dust emission things, there's a lot of calibrations that are based upon, I'm not an expert on this, but are based upon diffuse dust in the Milky Way and nearby translucent kinds of things, and maybe that's not generally, those calibrations, maybe they're not applicable in some of these other regimes. Bruce is not wildly, it's not like there's no way, go back and do it again. I mean, I think he's definitely like, he really wants, but I think given the uncertainties in that whole calibration chain, this is not, and the discrepancies, this is in exactly the same direction as every other discrepancy that somebody has noted in this regard, that I know of. There may be others.
Actually, I have a question about the high definition space.
Okay, yeah.
So is there an anticipated price tag for this thing? And please don't say 750 million.
Yes. Well, no, it's going to be circular, right? I mean, we're trying to figure out what do we need scientifically to make this compelling. Then that's a question of what technologies are available that can do this. Then it's identifying, the prices of mission go down if you do the technology investment early. Right. The problem is that if I say I'm going to do a flagship mission and all the technology I need is TRL1, okay, that's not going to go. The idea is that if you do investments now, so if you get the UV coatings, if you get that all hammered out by the next decadal survey, that's no longer a major price driver on stuff. So a lot of that, right now we're trying to figure out what areas do you need, what technologies do you need, and where to make those strategic investments to kind of bring things down. I mean, we don't want a mission that crowds out all other science, right? I mean, I don't think there's anybody, as much as I want to have this, I'm not that I'm a little selfish, but not that selfish an individual, that I would be happy that if this starves out, there's no other mission that NASA manages besides this, right? So put it this way, we are aware of it, but the technologists are optimistic that there are ways that we can handle this. And a lot of the people on the team are very, very experienced in taking stuff, both planetary missions, space missions of all sizes through. So there's a lot of know-how about where those kind of cost pressures come in. So I'm not going to quote you a number.
I was wondering, with the multi-wavelength data on M31, can you estimate the extinction law and the value of RV and compare that to the Milky Way value?
Yes, so this is something where, so Carl Gordon has been heavily involved in doing that spectral energy distribution fitting. And so this was work that Dennis Sawicki and Jason Harris were some of the first people to really kind of pioneer this on galaxy-wide scale in the Magellanic Clouds. And so the idea is that you know something about what stellar spectra look like, you model different extinction laws, and then you fit every star with some combination of models. And we're doing this all Bayesian, so we have error uncertainty distributions and all these parameters. And Carl's interested in exactly that question. And we do think preliminarily we see variations of RV with AV. So we'll never do an RV map with the same signal to noise as the AV map, but there certainly does seem to be a broad correlation there. So I think there will be results coming out of it, but we're just really trying to nail down the SCD fitter so that we really understand all of the systematics and everything. And it's hard because you really have to modeling the photometric uncertainties in crowded field photometry. The only way to do it is to make millions of fake stars, insert them in, recover them, and that's expensive. We have to do all this stuff on the cloud, and basically, anytime we press go, we're spending $1,000. It's just like such a big problem. We can't do this on just a little, computer in the basement, unfortunately. So doing the SED fitting means we have to do not just the original photometry, but we also have to do the full characterization of the uncertainties to make sure you're not biasing one way or another. So we're going to get there, and it looks promising.
Do you have infrared excesses or disks at all in your models, or is that just?
I think most of those pre-made sequence stars, I think, are kind of too faint for us to really pick up. Right? I mean, I don't think we're going to be that sensitive to pre-made sequence. Personally, what I'm really interested in doing is trying to get, there's precious little narrowband imaging at this resolution. And I think that there's actually going to be some really interesting stuff you can do in terms of symbiotic stars, Wolf-Rayet stars, BE stars. So I think line emission from stars, I think, is going to be kind of an interesting next step, but I don't think we're going to get down to like the really low mass young accreting populations. I could be wrong.
Last question, please.
Yeah. What about when you showed the two parallel red giant branches? I would have expected a continuum in between because some stars in front of the dust layer, some stars partly in, and some stars behind.
Right. And that was originally what we thought. Originally, it was. Going back to my Princeton, when I was at Princeton as a grad student, the ISM was pretty smooth, and it was in this nice hydrostatically supported layer, and that was going to be a full tomography effect. But in today's ISM, it's very clumpy. It's associated with the cold ISM, which has, all those features you see are on the scales of tens of parsecs. And so given that distribution of RGB stars was of the order a kiloparsec thick, stars are either in front or behind. So you may have isolated regions where there's a couple of clumps. A lot of those extinctions are pretty low. That's the other thing, is that the overall extinctions, in terms of those median extinctions, they're not super, super, super high. So a lot of what we're probably probing is going to be the cool ISM rather than the cold ISM. And in that case, there are interesting cases where we see deviations, where a foreground plus the log normal is not a good fit. And I'm following up those regions because I think those are interesting diagnostics of other things, such as depth effects, and also I think actually of internal structure within the cloud itself. So yes, I did think that, and there's an appendix in the paper that's like why that doesn't actually work. So.
All right, well, that's great.
Thank you.